Welcome to the deep dive. You send us the info, we pull out the essentials. The goal is to help you get smart, fast, without getting bogged down.
Exactly.
So today we're looking at Pipecat. Our listener, the learner, wants the lowdown on this system for building real-time AI applications.
Right.
We've got the tech docs, and we've looked at their GitHub activity too.
Good sources. Technical, but revealing.
And our mission here is basically to understand Pipecat's core architecture, its capabilities, and why its design is actually pretty significant for this whole real-time AI space.
Okay, let's get into it.
First thing seems to be this core design, the pipeline.
Yeah, the pipeline architecture, it's really central. Think of it like an assembly line, but for data.
Yeah.
Data flows through these stages and gets worked on at each step.
And the data moves in these little packets. They call them frames. I saw a comparison to network packets.
Precisely. Frames. Small, self-contained units. That's the currency of the system. They carry everything. Could be raw audio, could be the transcribed text from that audio, even just control signals.
So, like, if I'm talking, my voice gets chopped into these audio frames.
Right.
Which then maybe go to a speech-to-text thing.
A processor, yeah. A speech-to-text processor.
Yeah.
And that outputs text frames.
And it's continuous. That text doesn't just pile up. It flows right into, say, an LLM.
Exactly. Frame by frame. The LLM processes those text frames, generates its response as more text frames.
Which can then drive a text-to-speech processor.
You got it. Creating audio frames that you hear back almost instantly.
Right. That's the real-time streaming part. You don't wait for the whole thought to finish before the next step starts.
That's the magic. That incremental processing is what gives you that super low latency.
Yeah.
Makes the conversation feel, well, real.
Okay. And data usually flows downstream, input to output. But you mentioned an upstream path, too.
Yeah, that's important for control. Things like signaling the end of speech, end of stream, or if an error pops up.
Ah, so errors can travel backward, like a warning signal.
Exactly. It's a feedback loop. Helps manage the flow, handle problems gracefully, and processors are smart enough to just pass along frame types they don't recognize.
Oh, that's handy. So you can add new stuff without breaking older parts.
Right. Very flexible. Now, these pipelines, they're built from two main things: frame processors and transports.
Okay, frame processors. These sound like the actual workers, the ones changing or adding to the frames. The docs mention a process frame method.
That's the heart of it. Every frame processor has process frame. Takes a frame in, does its job, transcribe audio, call an LLM, convert text to speech, maybe filter things, aggregate data, whatever it's designed for.
And it can output 0, 1, or multiple frames.
Yep. Could filter something out completely, could transform one frame into another, or maybe one frame triggers several output frames. Lots of possibilities.
Okay, so processors do the work. What about transports?
Transports are the bridges to the outside world, the I/O gateways.
On-ramps and off-ramps.
Good way to put it. Input transports, like your microphone, or maybe a telephony stream from a phone call or a WebSocket connection. They take external data and package it into Pipecat frames for the pipeline.
And output transports do the reverse. Take finished frames and send them out, like playing audio through speakers or sending data over that socket.
Exactly. The daily.co WebRTC example fits here, handling the real-time audio and video for a video call.
Makes sense. And it seems you can wire these processors up in different ways, not just one straight line.
Right, that's another key point. You can have linear pipelines, sure, but also parallel ones.
Parallel. So you could process maybe audio and video frames at the same time on separate tracks?
Precisely. If you have different types of data coming in, you can have dedicated processing paths running concurrently. Huge for flexibility. Imagine adding image analysis alongside audio.
Yeah, that opens up a lot. Very modular.
It is. And Pipecat also has clever ways to handle urgent signals and errors.
The system frames, I think they called them like priority messages.
Yeah, exactly. For things that can't wait in the normal queue, like if someone interrupts or you need to signal the end of a turn quickly, they bypass the normal flow.
Like an express lane. And errors, you said they go upstream.
Right. Error frames propagate backward. This lets earlier stages, or even the original transport, know something went wrong and potentially try to recover or handle it. It's pretty robust.
Okay, that covers the high level. The docs also detail the specific modules. Let's dig into those a bit. Frames first. You said they carry data and metadata.
Absolutely critical, that metadata. Timestamps, unique IDs, essential for keeping everything ordered and synchronized in real time. And yet different frame types for different jobs: audio frame, text frame, LM message frame for AI interactions, end frame to signal completion. It's common language.
Standardized communication. Okay. Then frame processors again. We know process frame is key, and there are ready-made ones.
Oh yeah. Things like a Whisper DT processor using OpenAI's Whisper model, or an OpenALM processor to talk to GPT models. Saves you building everything from scratch.
Right. And the pipeline module itself, it's the conductor.
Pretty much. It orchestrates the frame flow between processors, manages the input-output queues connecting to the transports, and crucially, it enables asynchronous operation.
Meaning it can process data while receiving new input and sending output?
Exactly. No blocking, keeps things moving.
Yeah.
Which is essential for that real-time performance. It ties everything together.
Okay. And transports, we mentioned Twilio, daily, WebSockets, quite a range. They handle the specifics of each connection type, using special input and output processors.
They do. And they rely heavily on another component, serializers.
Serializers.
The translators.
Perfect word for them. They translate between Pipecat's internal frames and whatever format the external service or protocol uses. This is huge for integration.
So the core logic doesn't need to know about Twilio's specific audio format.
Nope. The Twilio transport uses a Twilio frame serializer that handles all that audio encoding, DTMF tones, hang-up signals, everything. It lets Pipecat speak many different languages without changing the core pipeline. Very clever abstraction. Okay, what about services?
Services are about integrating with the external AI providers, the actual STT engines, LLMs, TTS systems. Pipecat provides base classes and then specific implementations for OpenAI, Google, AWS, etc.
So a frame processor doesn't call the AWS API directly. It uses an AWS transcribe service instance.
Exactly. It keeps the processor focused on its task and abstracts away the specific API details. Much cleaner design. Separation of concerns.
Makes sense. And lastly, there are utilities and other helpers.
Yeah, a bunch of useful tools. Audio utilities for things like resampling or voice activity detection. Observers for like logging frame flow, metrics for tracking token usage or latency. Transcription helpers, they're the support crew, making sure everything runs smoothly and you can build robust applications.
Got it. So shifting gears a bit, what's under the hood, the tech stack?
It's Python 3.net and up. Big use of Asensio for all that concurrent streaming we talked about.
Essential for real time.
Totally. They also use type hints and Pydantic quite a bit, which helps with code clarity and managing configurations.
And you mentioned web server.
Yeah, fast API is in there, especially for WebSocket support, which is critical for real-time web comms. They use HTTPX for making those asynchronous calls out to the AI services. It's a pretty modern, solid stack for this kind of work.
What about audio and video processing itself?
They seem to handle some basics, but also integrate well with external services or standard Python libraries for the heavy lifting. They mentioned formats like YUV for video, suggesting they're laying groundwork there.
And the integrations. It's a long list.
It really is. OpenAI, Anthropic, AWS, Azure, Google Cloud, communication platforms like Twilio, Daily.co, Telmix, even things like Assembly AI, NVIDIA Riva, OpenRouter, they're clearly aiming for broad compatibility.
Makes it very versatile.
Definitely. And for the development side, they use tools like Lugaroo for logging. They're adding OpenTelemetry for tracing, standard stuff like Poetry or pip for dependencies, Rough for linting, PyTest, Docker. It looks like a well-maintained professional project.
Which probably explains why there's so much activity on their GitHub, looking at open issues and pull requests.
Yeah, it's very active. Gives you a great snapshot of where things are heading and what challenges they're tackling right now.
One big theme seems to be multimodal support. Video and images. Issues hashtag 1778, hashtag 1749.
That's a major frontier. Moving beyond just voice. Imagine AI that can understand what it's seeing and hearing in real time. That opens up huge possibilities.
Very cool. They're also working on streaming stability, looks like, especially for phone calls and WebRTC, issues about Twilio audio interruptions, hashtag 1771, and daily.co WebSockets, hashtag 1743.
Yeah, real-world reliability is paramount. Dropped audio, connection glitches, those kill the user experience. So it's good they're focused on hardening those core integrations.
And for the AI agent builders, they're refining LLM function calling. Issues hashtag 1735 and hashtag 1713 mention things like missing results or arguments.
Right. Function calling lets the LLM interact with external tools and APIs. Making that seamless and reliable is key to building truly useful agents that can do things, not just talk.
And then just a general stream of bug fixes and performance tweaks across the board. Issues hashtag 1741, hashtag 1703, hashtag 1694, ongoing refinement.
Standard stuff for an active project. Always approving.
But it's not just fixes, right? Lots of new features in the pull request, too. Open telemetry integration, hashtag 1729. Support for new AI services, hashtag 1639. Audio video handling improvements.
Yeah. Sequential function calls, hashtag 1683. More bug fixes, hashtag 1623. Even new sample apps for Android, hashtag 1755. And React Native, hashtag 1750.
Wow, so they're pushing into mobile examples too.
Shows they're thinking broadly about where Pipecat can be used. It really paints a picture of a dynamic, evolving platform.
Okay, so let's just quickly tie those core ideas together again. Frames, serializers, processors.
Right. Frames are the standardized data units, the lifeblood of the real-time flow.
Processors are the workers, using that process frame method, transforming data with that flexible pass-through behavior.
And serializers are the essential translators, connecting Pipecat's internal world to all the external services and protocols.
It seems like this whole architecture, the pipeline, the modular components is what makes Pipecat powerful for building these, complex real-time AI apps.
Absolutely. The modularity means you can swap things in and out, add new capabilities, new data types, new AI models, new communication channels relatively easily. It's built for extensibility.
So for you, the learner, the takeaway is that Pipecat provides this really solid, adaptable foundation. It handles the tricky parts of real-time streaming, plugs into tons of services, and it's clearly being actively developed and improved.
Definitely. Which leads to a final thought. We've talked a lot about conversational AI, but think about this architecture more broadly, this idea of breaking data into frames, processing it incrementally in pipelines, connecting flexibly to inputs and outputs. Where else could that apply?
Beyond conversation.
Yeah. What about, say, real-time monitoring in industrial settings? Or processing live financial data streams? Maybe even creating more responsive interactive game environments?
Interesting. Applying that same real-time modular approach to different kinds of data flows.
Exactly. What new things become possible when you can process and react information in that kind of fluid, interconnected way? Something to chew on.
Definitely food for thought. If you want to dive deeper yourself, the Pipecat docs and their GitHub repo are the places to go. Lots more detail there.
For sure.
Thanks for joining us for this deep dive.